Hello and welcome to this video on complex numbers. Now, complex numbers or imaginary numbers are something that you are first introduced to really in Further Pure 1, where you know that I equals square root minus 1, I squared equals 1, I cubed equals I squared equals minus 1, that probably explains. I cubed equals minus I to the 4 equals 1, I to the 5 equals I, etc, etc, etc. And you can go further by saying, well, if I to the 4 equals I squared times I squared equals minus 1 times minus 1 equals 1. Yeah, that's probably about, you know, the beginnings of what you did in FP1. Then you might have moved on a bit by adding some numbers, multiplying some numbers, etc. Now, I'm going to go through that first of all, and then I'm going to move on to some cool stuff which you can do in FP2, and then we're going to move on to some even cooler stuff that we can do in FP2. So, let's start at the beginning, shall we? We're going to do, I don't know, let's go and simplify some expressions. Let's do some adding, because everybody loves adding. Can we add these together? Now, the one thing you've got to remember with complex numbers is you've got to add like terms. So you can add integers, etc., or add numbers, and then you add your I terms, or your terms of I. So with this, it's 10 minus 2i, because you add the 8 and the 2, and you minus the 6 from the 4, etc. That's all we really care about. Now, I'm sure you can all add. Subtracting follows a similar method. Timesing together is also quite an important one, so we're going to run through that briefly. Now this is going to be quite fun, because remember, when you times I together, it's going to become I squared, which is going to become minus 1. So in this case, what we're going to have is we're going to have 64 plus 8i plus 16i plus 2i squared, which is going to go to 64 plus 24i plus, or should I say, minus 2. So we're going to have 62 plus 24i. So as you can see, all we've done is expand outwards. Now if you've got a posh graphical calculator, which may or may not be made by Casio in particular, you can do this on your calculator and it will save you a bit of time in your exams, especially if you're sitting FP1 again. Now here's something you won't have done really in FP1, and this is what we call long division, effectively. Division of complex numbers, or just simplifying them. So if we take the expression 3 plus I over 7 minus 3i. Now this looks quite similar to something else we did, mainly in Core 1. You know when you've got an expression you want to simplify it, or should I say surds, if I was to mention surds to you, it's, you know, we rationalise the denominator. Well, we're going to do exactly the same here. So we're going to times that by 7 plus 3i, 7 plus 3i. So 3 plus I, 7 plus 3i, 21 plus 7i plus 9i minus 3 equals 18 plus 16i. Then we're going to do 7 minus 3i, 7 plus 3i, 49 minus 21i plus 21i. And then what we're going to have to do is do minus 3i times minus 3i. So what do we have? Yeah, so minus 3 times minus 3 is minus 9i squared. So 49 plus 9 really. And that is going to give us 58. So what we now have is 18 plus 16i over 58, which we can just write as 18 over 58, which does cancel equal into 9 over 29. So we can just write this as 9 over 29 plus 16i over 58. And that is what is called, that's simplifying a complex number expression, which is something that you will need to get used to on how to do in FP2. Now, The first thing you will be introduced to in FP2 is modulus and argument of a complex number, and you'll use something called an Argand diagram. Now we won't go into Argand diagrams here, but we will go into how modulus works and how arguments work. Now, the modulus, if we say that every complex number is of the form x plus yi, the modulus equals root x squared plus y squared, and the arg, or argument, and funnily enough it is named after Mr. Arg, or Mr. Argand to say the least, is done by, or argument, equals tan theta equals y over x. So if we were to take an example, and we're going to go and do, we're going to go and do 1 plus I. Now the modulus of this is quite simple, it's one lot of I, so we can do square root of 1 squared plus 1 squared, so our mod is going to be equal to root 2. Argument is going to be tan theta equals 1 over 1, tan to the minus 1 of 1 is going to equal pi over 4. Now remember, we are in A2 maths now, we use radians. That's quite an important feature that you may or may not know. So remember, radians are the future. We're going to take one last example, and then I believe that you will understand arguments and modulus to a particular degree. So we're going to take 1a, or just going to call it 1a really, in case I decide to write more. 2 plus 2i, modulus will be 2 squared plus 2 squared is going to be root 8, and then we have arg, which will be 2 over 2. Ooh, how convenient, it works again. Tan to the minus 1 of 2 over 2 will still be equal to pi over 4. And finally, 1b, as I just like doing examples, 5 plus 12i. Now then, mod will be 5 squared plus 12 squared equals root 169 equals 13, and then we also have arg equals 12 over 5, so tan to the minus 1 of 12 over 5 will be 1.17, in case you get a decimal term. Anyway, that is how to do modulus and arguments in a nutshell. Modulus is simply get your x and y terms, square them, square root the whole lot, and then argument is doing your complex term over your real term, and then tan to the minus 1 it, inverse tan it, and that should explain how to do modulus and arguments. Thank you very much for listening.